Hi, I'm Don Davis from Lakeland Community College in Kirtland, Ohio, and I want to talk about the role of functions in pre-statistics. So what I'd like to do is to break this talk up into three parts. First, I'd like to talk for just a few moments about how I developed a pre-statistics curriculum and course, and then talk about our main objective here, the role of functions in a pre-statistics course. And then I'd like to conclude with just a few ideas on how we could incorporate functions in our existing introductory statistics classes. So let's go ahead and get started. I worked on pre-statistics starting back in 2010, and I think my impetus on that was the Pathways movement. This movement of trying to get students past this idea of going through a long string of prerequisite developmental algebra before they even get to their college level mathematics course. And the Pathways focuses primarily on StatWay and QuantWay, and I think CalcWay is included now. But I wanted to take a little bit different approach, and that approach came from watching students take introductory statistics I've been teaching that course for about 30 years in the college level now. And I noticed that certain students struggle with topics that are ancillary, that are tangential to the focus of statistics itself. And I feel like that impeded their learning of statistics. In other words, they kind of lost sight of the forest for the trees. So in terms of developing a curriculum, what I did was I just kind of did what I call reverse engineering. I asked myself, what are the topics in introductory statistics, and then what topics are needed to lead into those topics in introductory statistics. So a few years ago, I think the work that I had done to develop the curriculum was validated by this Dana Center document. I think many of you have seen this, Mathematics Prerequisites for Success in Introductory Statistics. So let me talk about that for just a moment here. And the focus on this document, Mathematics Prerequisites for Success in Introductory Statistics, really focused on 5 things. First, numbers in the number line. No doubt about that. We want to be able, for students to be able to differentiate between continuous intervals and discrete points on a line, and also to be able to have a student determine if a point is contained in an interval. So that's important for us. Also, operations on numbers, the simple order of operations. We see that come into play, in particular in when students compute test statistics. Some of them struggle with semantic errors, and also, we compute with complex fractions a lot more frequently in statistics than we do in algebra. So that's certainly an important topic. Equations and inequalities. Well, equations really is kind of a tangential topic to statistics. I mean, we use it to determine cutoff values, and that's really about it. But inequalities are critical for us, aren't they? To be able to differentiate on how inequalities are used for discrete data and continuous data, left and right tail tests, writing hypotheses, and that kind of thing. So inequalities are vitally important. Using sets, there's no question of the association between mutually exclusive events and disjoint sets, and how cardinality of sets is a gateway to introductory probability. So sets are clearly important. Also, graphing points and lines. I think a lot of students, they all remember how to plot 2 points and make a line, but don't necessarily know how to interpret average rate of change and that kind of thing. I'll talk about that a lot more later on, but that's certainly important. And then finally, simply reading tables and graphs. I mean, I think that's an important part of a pre-statistics course. Simply being able to read a chart and a graph. I mean, no matter what we do in statistics, we sometimes have to refer to a chart or a graph. And so what we want to do is to give students some practice in doing just that. And, it doesn't have to be statistical tables and graphs, but we just want to get them to get them used to looking at tables at the least. But the one thing that the Dana Center document didn't include was the use of functions, which is critical to us, in particular when we study discrete and continuous probability distributions. Now, so let me talk about statistics in a general, in a broad sense first, and then we'll get to the idea of functions here. So I think a common question is, what is pre-statistics? Well, first, let me state what pre-statistics is not. Pre-statistics is not traditional introductory algebra. I think many of you have seen that a class like intermediate algebra is certainly none of the topics there relate themselves to statistics. And as far as maybe a beginning algebra class where you simply work with linear equations, that kind of course helps a little bit, but it also can mislead students, and I'll talk about that a little bit later on. So pre-statistics is not traditional introductory algebra. And pre-statistics is not statistics. So in pre-statistics, we don't want to do things like doing measures of center and variation. We don't want to do density curves and that kind of thing. We want to we don't want to destroy the thunder for when students get to statistics and talk about that. So pre-statistics is not statistics either. So let me go ahead and define what pre-statistics is. We can say that pre-statistics is a preparatory course made up of a collection of topics from arithmetic, algebra, and geometry that are used to prepare students for a college-level introductory statistics course, while serving as an introduction to data-sourced applications. What we can do is to have students start to interpret solutions in a meaningful way before they get to statistics, and then when they get to statistics class and they want to do something like write a conclusion of a hypothesis test, well, they've already seen how that works. So let me start out with, in terms of functions now, what I'll call some presuppositions to motivate the topics of functions. Now, as I said before, the Dana Center document did not address functions, and in particular, no mention of functions is talked about in a statistical context. So let me give you a couple what I call presuppositions that students have as it relates to functions and how functions may relate to statistics. First, students' notion of functions is limited by the current algebra curriculum. If you really kind of think about it, students only think about functions in a certain way that we teach them, and really no further. Because that's the way our curriculum is defined. Our second presupposition is that statistics courses make latent presumptions about probability functions. I mean, if you really kind of think about it, we do make these assumptions and expect students to pick up on the idea of functions very quickly. I mean, many students can go into a introductory statistics course and never see a function at all because of their developmental curriculum that they were in. So let's address this first presupposition here, that the student's notion of functions is limited by algebra instruction. What I mean by that is that students are implicitly taught to believe that all functions are continuous with some rare exceptions. So you think about it. When we think about, we have students write the domain of a function. What are we having them do? We have them take out everything where a function is not defined, and everything else is the real line. Well, that doesn't help us for statistics, really. And the other part of this presupposition that all functions are algebraic in nature. In other words, made up of a ratio of polynomials and that kind of thing. So notice here's a typical function where we assume continuity, except at this one point, right? And this is just fine when we're talking about the idea of calculus, but insufficient when we're talking about getting a student ready for introductory statistics. And notice here, this is a piecewise defined function, so students think about functions primarily in terms of polynomials. And the problem with that is our second presupposition. Statistics courses make certain presumptions about probability functions. Let me show you what I mean. Here's the first function that most students see in an introductory statistics class. So think of what that is. That's most likely the probability mass function, or you might call it the point density function, for the binomial distribution, for a binomial random variable. So they'll be sitting in class one day, then they'll see this. And we tell them, this is a function. This is a probability mass function here. And think of what goes through a student's mind here. First, they say, what's this mean? I mean, really what we're saying here, and you know all this is the probability that a binomial random variable x takes on the value x. All right? They don't look at it that way. It just says x equals x. And so that has to be explained to them. Or they might say, where's y? Or some students who have had some introductory, maybe college algebra, if not intermediate, said, might even say f of x. So that's kind of getting there, but they don't see any of that because it's written in terms of a probability function. And then they'll ask, what's this stuff right here? What's up with this? I'm used to looking at intervals and inequalities when it comes to a domain of a function. All right? So notice here, that's just in terms of function notation and the domain in which this function is defined. We didn't even talk about, something like this, where we talk about the combination being used, nor did we talk about an exponential function where, notice here, the independent variable x is in the exponent. All right? So there's really a lot to do. And this is what I mean about these latent presumptions about probability functions. So let's start out and take a look at how we compare and contrast an introduction to functions in pre-statistics. And I think one of the first things we want to do is to contrast the idea of relations and functions, not just in a continuous sense, but also in a discrete sense. Let me show you what I mean. In the continuous case, you often see this kind of thing with the vertical line test, right? Where we say, if you draw these vertical lines through a graph, if it hits it more than once, then the relation is not a function, right? Well, it's also just as legitimate, and something we want to do in pre-statistics is to have students think about this in the discrete case. In other words, let's say we have a scatter plot like this, a plot of points. Notice here, this point and this one share the same vertical line. Same thing with these, and this third pair here. So the first thing we have to do is to convince them that if you have a series of points, you could have a function, and that's certainly a big deal. And second, how to determine if a sequence of points on the xy plane determines a function. So that's the first thing I think we want to get through these students in pre-statistics in terms of functions, just to get them started thinking in a statistical context. I guess the next topic would just be, again, going with what we do in algebra, but in a statistical context, talk about domain and range. In pre-statistics, we define domain and range just as we would in an algebra course. But the emphasis is on identifying the domain and range from values given in a tabular form. And this helps us to get across the notion of discrete probability, to, in other words, foreshadow discrete probability. So it makes that transition to discrete probability distribution functions much smoother if we can kind of relate the idea of a table. Let me show you what I'm talking about here through an example. Let's do this. Let's write the domain and range values for the following table of values. So notice here our simple x and y values. And again, this is pre-statistics here, so we're not talking about defining a discrete random variable of any kind. And notice here the values of x are really kind of what you'd see for a discrete probability distribution, whether it be geometric, Poisson, binomial. But notice down below where the y values are, the dependent values are, notice those values kind of look like probabilities, don't they? At least, and we're not going to say that, but at least we're starting to get students to look at things in a statistical manner. It also just happens that all these y values add up to 1, which is kind of nice as well. So students can look at this and they can say, well, there's our domain, these discrete values, and here's our range, all right? All of these y values that correspond to it. So something as simple as domain and range can be used to motivate, to start to get students to think about the idea of statistics. Now let's get to the graphing part and talk about that a little bit. In algebra courses, functions are taught in the context of continuous functions. Everything is continuous. The problem is, the first time they try to evaluate a function over a discrete domain, they don't know what to do. Now let me just take a moment to talk about this a little bit. I mean, I think something that one might think you could do is to use this idea of the co-requisite model. All right? I'm not a fan of this. I think some of you who have been going to conferences for a while might remember about 20 years ago, this notion of just-in-time learning was very popular. All right? Notice, if you didn't hear about that, that's because, well, that notion kind of failed. The co-requisite approach is really just-in-time learning under a new name. The problem with co-requisite learning is it's somewhat of a derail. It takes students off topic. And by the way, let me just digress for a minute and just mention one of the things that I think we should teach in pre-statistics is permutations and combinations. That is something I see as somewhat of a derail topic when we get to probability. A lot of times we talk about doing a lot of doing the probability rules, teaching students how to use contingency tables, teach students about conditional probability, and then at the end, well, we talk about permutations and combinations and the multiplication rule, and then we go into talking about discrete probability distributions. That's somewhat of a derail, I think. So I think that idea of counting techniques is really a pre-calculus topic, so we can free up some of that time that we can use better when we teach introductory statistics. So not a fan of co-requisite model. Also, it's really kind of time consuming, and it's hard to know what students need this co-requisite knowledge of and what they don't. So I'm more of a fan of the tried and true prerequisite model, but just make it brief. Make it a one course prerequisite. All right, but I digress there for a minute. Let me get back to the idea of graphing functions on a continuous, on a closed interval where the function is continuous. So how about this? consider this function, f of x equals 1 plus 0.3x, and I'll talk about that format in just a moment here. Evaluate f of 0 and f of 5. So let's go ahead and get going on that. There's f of 0 there. F of 0 is 1. And then we have our other point, f of 5, that's 2.5 when you plug in 5 into our function here. And then we can just simply graph the function by connecting the points, right? So you might think that's a very simple thing, but to get the idea in students' heads that they want to graph functions on a closed interval not only helps us when we talk about probability, but more importantly, helps us when we get to the idea of linear regression, where we really want to specify that a regression model is defined over a closed interval. Now, let me do another example from PreStatistics here. We talked about graphing a continuous function on the closed interval. Let's talk about graphing the same function in a discrete context. So how about this? Have the same function. Let's make a table of values for x being the whole numbers from 0 to 5. So there they are right there. All right. So just the typical T table, as we call it, right? And then let's go ahead and plot these values. So notice here. We can go ahead and start plotting here. Here's the first point, 0, 1. And then 1, 1.3. And now students start to see the idea that you don't have to always plot a graph in terms of a line segment, but we can have a sequence of points in R2, in the XY plane. All right? So if we can just get this idea across, that you can take a function and graph it over a discrete domain, that is real helpful for when we get to the discussion on discrete probability. Now, let me talk about the idea of how we treat linear functions in PreStatistics. Students are always taught this slope-intercept form, tried and true. I'm sure this is what you had when you were a kid, right? Y equals mx plus b. The only thing is, this is not used in statistics, right? We always use this statistical form of a line, f of x equals a plus bx. Now, you can probably write it different ways, right? You might see this, y prime equals a plus bx, or e equals a plus bx. You might see y hat equals b sub 0 plus b sub 1x, all right? But it all has the same form where we have a constant and then a linear term, and not the other way around like we do with the slope-intercept form. So this is a common point of confusion for students. So if this is one of the things we really want to try to get across in a PreStatistics course. I think the natural question is, what's our motivation here? Why would you want to write the statistical form of a line? Well, I'll offer up a couple of ideas here of why that would be true. First, the statistical form of a linear function offers a simple expansion for higher order polynomials. You know? So if you want to do a quadratic regression model, we can write that as a plus bx plus cx squared. For a cubic, add on dx cubed. You don't have to do all that shifting around of coefficients. All right? So that makes higher order polynomials easier to write. And it's also true for multiple linear regression models. So you could have something like this. B sub 0 plus B sub 1, X sub 1, B sub 2, X sub 2, and just keep adding those independent variables as we go along. So for those two reasons, I think it's much easier for students to use the statistical form of a line and know that before they get to their statistics class. Now let's compare and contrast these two types of functions. First, the algebraic form, and then the statistical form. The algebraic form has the tried and true y equals mx plus b, as opposed to the statistical form a plus bx. Slope is m for the algebraic form, and the marginal change is b. And I'll talk about that a little bit more later, all right, about this notion of marginal change. X is the independent variable with the algebraic form. In statistical form, we call x the explanatory variable, don't we? So it's nice if we can introduce that kind of language before students get to statistics. Y is the dependent variable, and think of what I'm going to say over here. I'm going to say y is the response variable in statistical form. And then finally, and I guess this leads to a little bit of confusion, so we have to take a minute to talk about this. The y-intercept is at 0b, and this is always one of my pet peeves, I guess, a little bit, is that, right here, the y-intercept is a point. It's just not a number. A lot of times students say, well, the y-intercept is b. Well, it's really an ordered pair, isn't it? As opposed to the statistical form where the y-intercept is at 0a. All right? So that's how we can contrast the statistical form and the algebraic form. Now let's take a minute to take a look at an application of using a linear model in PreStatistics. So how about this? The shoe industry has seen steady growth during the last decade. And here's a quote from Footwear News. We've seen a meaningful increase in the percentage of sales in running, basketball, and casual categories. The sales of fitness shoes in the U.S. from 2000 to 2014 can be modeled by this linear function here. 22.17 plus 0.57x, where x runs from 0 to 14. So here, x represents the number of years since 2000, and f of x represents the annual shoe store sales in billions of US dollars. All right, that's some information I got from the National Shoe Retailers Association. So here's what we want to do with this. Evaluate and interpret f of 13. All right, so we not only want to evaluate it, the plug and chug part, we also want to interpret what this means in the context of the function we're given. All right, so here's our function. We want to evaluate f of 13, right? So it's always good to introduce the word evaluate. When students hear the word evaluate, they don't think plug and chug. They think, taking a test or something. So at least that language is new to them. So what do we get there? 29.58. And now the important part, the interpretation of the meaning. Now, we said that x represents the number of years since 2000. So we can interpret that as, according to the model, in the year 2013, the shoe store sales were about $29.58 billion. So notice here we have the correct time units, and we also have the units on the dependent variable, the response variable here. All right? A couple of observations here. In our second part, if the value of x increases by 1, how much do the annual sales increase? In other words, according to the model, as each year passes, how much do the annual sales increase as the function is defined for this interval from 2000 to 2014? Well, that's pretty easy to do, isn't it? Right? Rise over run. Remember that? It's given by the marginal change. All right? Which is, in this case, is 0.057. So notice here, this number, 0.57, happens to be the coefficient of our explanatory variable. There it is right there. All right? So let me take a minute to talk about that, and because that's one of the points of emphasis we want to have when we talk about linear functions in pre-statistics. We can say that if the X value increases by 1 year, the shoe store sales increase by $0.57 billion. So that's our interpretation of the coefficient of the X variable. And I think that's important to recognize, because this is something that we often emphasize in statistics, but we never talk about it before statistics. And it's so obvious, I think, for students to understand. All right? So notice here that if we take f of 13 plus the marginal change, we get 30.14, right? So let's take a look at this graphically here. There's 13, 29.58. Add on the marginal change, we get up to 14, 30.4. So what did we do there? We increased X by 1, so the change in X is 1, and then the marginal change increased by 0.57. So let's go ahead and offer up this definition for students in a pre-statistics course. We can say that the marginal change is the increase or decrease in the dependent variable value as the independent variable value increases by a single unit. All right? So we can go ahead and not wait till statistics before we define marginal change. We can do it right here in a pre-statistics context. Now let me talk about one other thing where we want to kind of get students set up, at least in the back of their mind, for, in particular, discrete probability. As we said before, algebra students are introduced to piecewise defined functions in the context of continuity. All right? So when it comes to piecewise defined functions, students are looking for continuity. They're latently looking for left and right limits, but we don't talk about that, do we? Till we get to calculus. So we'd be looking at that point right there, that point of breakage, so to speak, that jump in the line at x equals 2. But in statistics, piecewise defined functions are used to identify what I call exclusivity. Let me show you what I'm talking about here. And I'll just go ahead and define a geometric random variable. So here we go. We can say for a geometric random variable, x, with the probability of success being p, and the number of trials before the first success x, the probability mass function is given by, well, here it is right here. This is really what it is, isn't it, if we think about it? It's not just the top line, but for any values other from 0 up to our terminal point, n, the probability is 0, right? Probability that x would be square root of 2, 0. Probability x would be 3/2, 0. So this part here is the exclusivity part, the 0 otherwise. So this gets students thinking in a statistical context without doing statistics. All right? So that's something we want to get across in our students' minds when we start to get them ready for statistics class. One other thing. I think it's important to talk about the vertical distance from a point to a line. Let me show you what I'm talking about here. We can say that for a linear function model, f of x equals a plus bx, with the estimate being, x of x sub e, f of x sub e. That's our estimated value from the regression model, and the actual value, x sub e, and then I'll call it y, the actual value. The vertical distance b is given by what? Well, think about it. It's the absolute value of the difference between our estimated value and the actual value. All right? I guess in the context of how we defined it there, that would be the absolute value of the difference of f of x sub e minus y. Graphically, it would look something like this. You'd have a model involved, a given point, There it is right there. And that's on the line, so that would be an estimate. There's a point off the line. That's our actual value. And we want to compute this vertical distance at d. And that's exactly what this formula gives us, isn't it? And think of why we want to do that. Think of why we want to talk about the vertical distance from a point to a line. We can use this computation as a segue to talking about residuals when we get to linear models and talk about explained and unexplained variation. So in pre-statistics, we can go a step further. We can talk about the percentage error of estimate from a function model, and we can define it this way. The percentage error, PE, is the absolute error, and then we just multiply it by 100 and put on a percent sign, right? So this is the relative error, right? And it's absolute, so we take the absolute value and then make it a percentage to get the percentage error. So finding the distance from a point to a line, that's great. We can also talk about the percentage error of estimate, and we can set up a guideline. It could be a 5% guideline to see if an estimate is a good one. Could be a 10% guideline, depending on the context of the data you have. But at least we're starting to get students to think about the idea of an estimate and an actual value, the error between the two, and the percentage error. All right? How good that estimate is. Now, let me talk about certain kinds of functions and how we can really get to some ideas that I think would help students when they get to statistics here. The idea of constant functions. All right? First off, two cases here. First, the continuous case, which would look something like this. F of x equals k on a closed interval from a to b. 0 otherwise, because we wanted to define that exclusivity part. So there is our function right there, right? And we get a line segment of the length b minus a, right? In other words, the right endpoint minus the left endpoint. And we can contrast that with the discrete case, and it would look something like this. It would be the same, except notice here the domain is defined differently. I put x sub 0 and then x sub 0 plus 1 and so on up to some terminal value x sub n. Function value is always k. So think of what we get in this case. Have our values defined from x sub 0 to n, and we get a sequence of level points, horizontal points, if you will. All right, so it's first good to talk about the idea of constant functions in pre-statistics in both the continuous and discrete case, because if you really kind of think about it, this makes computation of the uniform random variable a lot easier, because that's certainly something we can talk about in both a uniform random variable. We can talk about a discrete uniform random variable and also a continuous uniform random variable. And if we contrast that in pre-statistics, that makes that notion even easier when they get to their introductory statistics class. And the reason I think that constant functions are important is that they provide a motivation. Because if you really think about it, what we have to do is to teach integral calculus to by and large, non-STEM students. And we have to teach them how to integrate without knowing anything about integration. All right? So I know we don't like to talk about that, but at least we want to motivate it. I mean, it really kind of gets to me when I hear professors say, something like, well, this is beyond the scope of this course. Well, it shouldn't be. We should be able to talk about it in a meaningful fashion. So let's talk about how we could go about teaching students some calculus without them knowing any calculus. All right? And I think if you've taught an applied calculus course before, you'll know what I'm talking about here. Relating the fundamental theorem of calculus to a constant rate function. So let's go ahead and set that up now. Let's let y equal to a plus bx represent a linear model. So in other words, we have a linear function here, and without loss of generality, I'll let that function be an increasing function here. And let's let y prime, let's think about it here. If y is a plus bx, the derivative of y with respect to x would be b. And we'll let y prime equals b represent the corresponding rate of change function. I'm not going to call it a derivative. That's a little bit too much of calculus. Let's just call it a rate of change function. Or we can just call it a rate function if you prefer. And let's go ahead and graph that. That would just simply be a constant function, wouldn't it? Then, by the fundamental theorem of calculus, think of what that means. That means if we take the area under our rate function on this closed interval from x sub 1 to x sub 2, that area is going to be equal to the difference of our two function values of y. In other words, y of x sub 2 minus y of x sub 1. And that's exactly what the fundamental theorem of calculus gives us, doesn't it? You know, in effect, the derivative and the integral are inverse operations, so to speak. All right. But we're not going to, you know, all these slides you see in this green tint, we're kind of going under the hood, where I kind of explain to you the motivation behind this. Now let's take a look at and see what the student would think of when they do a problem like this. When we talk about determining the area under a constant function, and this is where we use some ideas from geometry. Let's consider a constant function of the form f of x equals k, defined on a closed interval from a to b. So let's take a look at that. There it is. And now, the area under A, the area A under f, on this closed interval from x sub 1 to x sub 2 is going to be given by, well, that's simply the area of this rectangle here, isn't it? So that's going to be, you know, base times height. So that would be the base, that's the difference between the right endpoint and the left endpoint, times the height. Height is simply the function value k. All right? Where x sub 1 and x sub 2 are contained in this closed interval a to b. And that's another thing when I talked about those prerequisite topics from the Dana Center, the idea of containment in the closed interval I think is important to always look at here. All right, let's take a look at an application of determining the area under a constant function here. The boom of social media, affordability of smartphones, and availability of online video have contributed to rapid growth of the internet on a global scale in the 21st century. Now, the information I found on this came from CIO Today, Chief Information Officer. We can see that the rate of increase in the number of countries with over 10 million internet users can be expressed by the function, there it is right there, constant function 2.4 on the interval from 0 to 11, 0 otherwise, where x represents the number of years since 2000 and f of x represents the rate of increase in countries with over 10 million internet users in countries per year. All right? And that would be how we would define the dependent value. Compute the area under f on the interval from 6 to 11 and then interpret the result. So in other words, we're given a rate function here. All right? Every year, the number of countries with over 10 million internet users increases by a little bit more than 2. All right? Let's go ahead and interpret this area now. So here we go. First, we'll graph the function. So the independent axis, the explanatory variable, years since 2000. Dependent values, increase in countries with over 10 million internet users. And notice we're talking about increase because this is a rate function. There it is, 2.4. Now I went ahead and put in the 0 otherwise part. You see that little line right there. And so think of what we're finding here. We're finding this area where x starts at 6 and ends at the right endpoint at 11. All right? So we seek the area of that shaded region. So let's go ahead and do that now. And that's pretty easy, isn't it? I mean, it's obviously easy for you guys, but you know, it's certainly not obvious to students. So let's take a look at that. So the area under f on the interval is given by, let's see here. Here's our graph. Here's our function. Here are the 2 points. And notice here I included the 0 otherwise part. There we go, on both sides. There's the area we seek. So that's going to be what? K. And then the difference, right endpoint minus left endpoint. So we get 12 square units. All right? But we want to interpret this in the context of the rate function we were given. So this means that from 2006 to 2011, and that's what the 6 and the 11 meant, 12 additional countries acquired over 10 million internet users. All right, so that's how we can use a rate function, teach calculus to some statistics students before they get to statistics. All right, and the other thing too is that when we do continuous uniform random variables, students won't be bewildered by it. They'll know exactly what to do. All right, another thing we can do with constant functions is help compute cutoff scores, cutoff values, if you will. Let's take a look at that. We can say that for a constant function, we can determine the cutoff value, and I'll call that x sub 1, so that either 10, 5, or 1% of the area is to the right or to the left of some given value x. So let's say we have a function that's constant, that's defined on a closed interval from a to b. There's our constant function there, f of x equals k. Its area is a. Let's say we want to take k% of that area. We can find this value, x sub 1, by determining the cutoff value. And the idea, the idea is obvious here, right? We can also talk about the notion of critical values and p-values once we start to talk about the idea of a cutoff score, so to speak. All right? And let's just try one of these, all right? Let's say we have a constant function here, f of x equals 5. And let's define that on a closed interval from 2.5 to 8.5. And let's do this. Let's find the value, x sub 1, which yields the rightmost 10% of the area under f. Well, I guess the first thing we have to do is to find the area A, right? So the total area is given by right endpoint minus left endpoint times the height, so we get 30 square units. And then we want 10% of that, so that would be 3, wouldn't it? So we want to find the x value, so that the area to the right of that x value is 3 square units. So in other words, we have to solve a little equation here, right? We want to use that area formula. We know the area. We know the right endpoint, that's 8.5. We don't know the left endpoint, but we do know the height. So we can just plug all that information into our area under a constant function formula. And here it is. 8.5, the right endpoint, minus the desired cutoff value, x sub 1, times our function value of 5 equals 3. So, let's see. If you solve this algebraically, you end up with 7.9, it looks like. So if you put in 7.9, that will give you 10% of the area under our constant function there. So I think that's a terrific way for students to start to think about the notion of critical regions, critical values, and p-values, all right? Because, students just don't get the idea, I don't think, that a p-value represents an area. Now, I don't want to go into all the stuff on, like what the ASA says about what a p-value is, because I read all that and I, kind of shake my head. It seems like they've kind of taken a simple idea and made it difficult, I guess. Now, let's take this idea of the area under a rate function and extend it now. Not to a constant rate function, but a linear rate function. So let's think about that now. Let's let y be a quadratic model. In other words, of the form a plus bx plus cx squared. Its corresponding rate function would simply be y prime equals b plus 2cx, right? That's the derivative of y with respect to x. So here's our quadratic model. And here is our corresponding rate function, our rate of change function, so to speak. And think about it here. Notice here, this quadratic function we drew was concave down. That means the derivative will be decreasing in this case. So what do we know here? By the fundamental theorem of calculus, if we integrate this rate function on a closed interval from x sub 1 to x sub 2, that simply gives us the difference of the function values for our given quadratic model. And let me show you that diagrammatically here. So here are our two values, x sub 1 and x sub 2. So the idea here, what the fundamental theorem of calculus gives us, and again, like I said, if you've taught applied calculus before, this is really not news to you, is it? That this area under this rate function is the same as the difference of the function values on our quadratic model here. Now notice here we have to be a little bit careful about where we define the model, how the model works. I mean, we can easily get into a discussion on the difference between gross and net areas. We don't want to do that. We want to try to kind of keep one idea at a time going here. All right. Let's take a look at an application of one of these. So let's see here. How about this? Oh yeah, I guess we ought to talk about how we could define the area under a linear function on a closed interval. Let's do that. Okay, so let's say we have a linear function of the form a plus bx defined on a closed interval from a to b. So let's go ahead and draw that here quickly. There it is. All right. Then the area A under F from x sub 1 to x sub 2, this closed interval, is defined by, well, what? The area of a trapezoid, isn't it? Right? So in other words, it's going to be the average of the bases times the height. Now you have to kind of think about it here as, kind of an unconventional way to look at it. The two bases here, the two parallel sides, we want to take the average of those. That's the f of x sub 1 plus f of x sub 2 over 2, right? So that's the average of the lengths of the bases, and then we want to multiply by the height, all right? And that's going to be the right endpoint minus the left endpoint. So base times the average of the heights. You can think of it that way. All right, let's apply this now. How about this? Sales of organic food has increased rapidly in the last few years. And here I found a quote that said, someone said, the demand for organic foods seems to be unquenchable. All right? It's kind of weird to use the word unquenchable. That's like thirst. It doesn't have anything to do with food. I found that kind of an odd quote. So I found that the rate of increase in organic food sales from 2006 to 2016 can be modeled by this function here. And notice, we have a linear function defined on a closed interval, and the y-intercept here is at 0, negative 6.43. So this kind of gets students to recognize the idea of what we call in applied calculus a reasonable domain. All right? You know, it would be impossible to put in 0 there and have a meaningful interpretation of it. In this case, x represents the number of years since 2000. F of x represents the rate of increase in organic food sales in billions of US dollars per year. So in other words, to digress for just a moment here, the marginal change concept tells us with each passing year, we gain about 1.25 billion of food sales in organics. Let's calculate the area under f of x on this closed interval from 10 to 15 and interpret the result. So here we go. Here is our function. There it is. Negative 6.4 plus 1.26x. Now, knowing our function values, f of 10 is 6.17 and f of 15 is 12.47, those function values, the area then is going to be given by what? The difference from right endpoint minus left endpoint, and then we want the average of these heights, don't we? Right? So we'll take 1/2 of the sum of those two function values, and we get 46.6 for our area. And now the important part, the interpretation. This means that from 2010 to 2015, the sales of organic foods increased by 46.6 billion US dollars. So notice we have two things going on here that are preparatory topics for introductory statistics. One, area under a curve. All right? You can think, if you kind of squint and take a look at this, you can think of this as the standard normal curve, and we've highlighted the area from -1 back to -2. You can kind of think of it that way. And I'll talk about that a little bit more here in a minute. And also, the idea of interpretation for models, all right? If we can interpret a model like this, that makes doing interpretations of probabilities easier, and interpretation of estimates for regression models easier. And now, I just mentioned this. I want to talk about how we can mimic the normal distribution in the context of pre-statistics. We can use what I call a triangular function to mimic some of the properties of the density function for the standard normal distribution. So it's just a great way to practice calculating probability style areas. All right, there's the function right there. All right, piecewise defined function. The first piece is increasing, going from the interval -3 to 0. The second piece is decreasing. Notice there the slope is negative, and that piece goes from 0 to 3. So when we graph this, let's see what it looks like here. There's our function. There's the horizontal axis. There's the vertical axis. here's the first piece. Here it goes up to the top there. And that would be 1/3 would be the y-intercept. And then there's the second piece that decreases. All right? So we get a triangular style function. So it's kind of a, I don't know, mesocurtic, I guess you could call it. All right? In a loose sense. So notice here, this is rigged up so that the total area under f on the interval from -3 to 3 is 1. Certainly one of the properties of a probability density function, isn't it? Now let's do an application of this triangular function here. And I call that big F of x. Calculate the area to the left of x being -2. Okay, well, we can do that, and we can just use our area under a linear function formula. This is just a special case of that, isn't it? So first we'll draw our triangular function here. There it is, big F of x. And then we want the area to the left of -2. In other words, that little tail right there, so to speak. So the area is going to be given by, well, I'll spare you the arithmetic, but notice there we get 1/18. So if we take 1/18 of the total area under the curve, notice there we get a little bit more than 5.5%. All right? So we can start to build up the notion of p-value, of critical regions, before the student even walks into a statistics course. All right? And notice here, the formulas are there are just very few formulas in pre-statistics, and this is one of them. Now, we can also get students ready for regression modeling by just kind of doing, I guess what we can call a survey of functions. All right? We can introduce common function types to motivate multiple linear regression models and nonlinear regression models. And the impetus here isn't on what we do in algebra class, where we talk about all the different properties of exponential and logarithmic models and that kind of thing. We don't do all that stuff with polynomials and find removable discontinuities. We're not worried about all that. We're not worried about terminal behavior either. Simply identification of a function type and evaluation. All right? First, for multiple linear functions of this form here. The important thing is for a student to be able to recognize one, to see what it looks like, to perhaps talk about the idea of explanatory and response variables, and that these b's we see here are really coefficients. They represent fixed values. So the objectives here are to identify, evaluate, and interpret the function. That's really all we want to do. Let me go ahead and do an application here. How about this? Determine if the functions represent multivariable linear functions here. So I'll give you a couple of functions, and this is what we'd want a student to do. Take a look at that one. Well, that has two explanatory variables, and they appear to be linear. The only thing is, well, they're rational, right? They're the ratio of variables, right? So because x sub 1 is divided by x sub 2, we see that this is not a multivariable linear function, as opposed to something like this. Now, one thing I wanted to mention here is take a look at this notation, f of x sub 1 comma f of x sub 2. Here's a perfect time to introduce this kind of function notation, so that when students get to a statistics course, they're not derailed by it. They're not thrown off by it. They're all ready to see how it works. So notice here, this meets the definition of multivariable linear function, so we're all set to go on that one, aren't we? So there's the identification part that I was talking about. Now, as far as graphing multivariable linear functions, well, I guess we can do some of that, right? we can show functions with just two explanatory variables and just talk about the idea that these functions can be graphed in 3 space, in R3, in 3 dimensions, the XYZ plane. All right? And I think that that's what we want to do, is to first talk about how we want to, when we get to statistics, talk about how these are graphed in the first octant. Or so the values of X, Y, Z are all non-zero. Now, you might wonder where I got this graph. If you just type in plot and then an expression in the Google browser, it'll plot that function for you, just like the one you just saw here. All right? And that is an example of one of the functions that this function here is graphed right there using the Google Chrome browser. So students don't need a special piece of software. They can experience that just by using their browser. Nothing special. In terms of polynomial functions, you know how it is in algebra class. We pound students over the head with polynomials. Now, students are probably familiar with, cubic models. They're certainly familiar with quadratic models because we emphasize it so much. And the emphasis in pre-statistics is not, the quadratic formula. It's not the parabolic shape. It's not finding intervals of concavity or anything, but simply form and extrema. All right? To be able to recognize a quadratic function and the fact that they have exactly one extrema, in other words, one minimum and one maximum function value, and a quadratic function has exactly 2 extrema, exactly one minimum and one maximum function value, by and large. Now, there are certainly exceptions, right? For example, just the parent function for a cubic function has no extrema, but we're talking about it in more of a broader sense here in a statistical context. All right? Now, one thing we can do in terms of nonlinear functions is to talk about power functions. Of the form a times x to the b, because this introduces a concept that students don't get. If they look at a triangular function, they can start to think about the normal distribution a little bit, but what that lacks is the notion of concavity. We can take a look at a power function like this, where the value of b is a proper fraction. That is concave down. If we take a look at the graph of a power function where the exponent is bigger than 1, those are going to be concave up. And without loss of generality here, we're assuming a is a positive value here, right? So once this formal definition of concavity is established, and it's easy to talk about how, it's smiling, it opens up, it holds water. However, it will hold water if it's like a bowl. However you want to talk about concavity, concave down is like a frown, that kind of thing. We can tie that in, concavity, to the normal distribution when we get to our statistics class. Here's the standard normal definition. We can talk about the region where the graph is concave down and have that have some meaning because students have studied power functions in pre-statistics. Here it is concave up on these 2 regions. And once we talk about concave down and concave up, it's just a short extension to talk about the notion of inflection points. And where are those inflection points on the standard normal curve? They just happen to be exactly 1 standard deviation away from the mean. So we can talk about the notion of inflection points once we talk about concavity, and that really gives students a heads up. Again, we're teaching calculus, but in a non-analytic fashion. Now, I think another thing in terms of nonlinear functions, something we want to talk about, is the natural exponential function. All right? So in other words, introduce the value of E. So many students, if they haven't taken, college algebra or haven't had it in a while, don't remember what E is. All right? So what we wanted to do is to develop what I call an operative understanding. And the reason, certainly it helps with the normal distribution when we talk about if we just even write down the probability density function for a standard normal random variable. But we can also talk about the idea of the Poisson distribution, where we use E, and the exponential distribution as well. So let's take a look at an application that involves an exponential function here. How about this? A naturalist determines that the relationship between the length and weight of a sturgeon can be modeled by, there it is right there, 27.7 e to the 0.008x on the interval from 250 to 500. X represents the length in millimeters, and f of x represents the weight in grams. In case you didn't know, a sturgeon is a type of fish. So let's do this. Giving this exponential function here, what did we say? One of the points was evaluation. We simply want to be able to plug and chug. Estimate the weight of a sturgeon that is 300 millimeters long. So in other words, evaluate f of 300 and interpret. So there it is. We did our plugging and chugging. And so that means, in terms of an interpretation, that we expect a sturgeon, not a student, but a sturgeon, that is 300 millimeters to be 305.3 grams according to our exponential model. So how about this part? Knowing that the actual weight of a 300 millimeter long sturgeon is typically 312 grams, calculate the percentage error. So notice here, and we talked about this a little bit earlier, the notion of percentage error, the difference between estimated weight minus actual weight divided by the actual weight, and then we make it a percentage, so we get a percentage error of 2.1%. And as we said before, we can talk about the notion of a rule of thumb for good estimates, and this would certainly qualify as a good estimate, I would think. So let me wrap things up with just a couple ideas where I think we can use functions a little bit better in introductory statistics. So traditionally, the use of functions is really, I think, underutilized in introductory statistics courses. Beyond their use for calculating discrete and continuous probabilities, they can also be used for critical thinking skills. All right? Let me show you what I'm talking about. First off, something as simple as Chebyshev's theorem. We can say that for any set of numerical data, at least p% of the data lies within k standard deviations of the mean. Now we can write that in function form. We just don't have to put down this relationship. We can write it in terms of a function. So notice here, I've written this as a function of k. K is the independent variable, p is the percentage, the portion, so to speak. And notice I multiplied by 100 to make it a percentage. And remember, this is true. Chebyshev theorem applies when we are at least one standard deviation away from the mean. All right? We are more than one standard deviation away from the mean. So you graph that function and you get this. We can get across a couple of ideas here. There's our function. How about this? The notion of a horizontal asymptote. All right? Where we can talk about how the function gets closer and closer to 100% as the distance away from the mean increases, but it never touches that. All right? And we can take a value, for example, like 2. Plug it into our function and get what? P of 2 is 75%, meaning at least 75% of the data lies within 2 standard deviations of the mean, no matter what the distribution of the population data is. So there's a way we can use a function to gain insight. So you can get a function curve, and we not only can talk about k-standard deviations away from the mean, where that value is discrete. That's what we usually do, isn't it? 2 standard deviations, 75%, 3 standard deviations, that's what, 8/9 or 88.9%. All right, we can talk about 2.1 standard deviations away from the mean, that kind of thing, and have that have a contextual meaning because we talked about it in terms of a function. Also, how about the minimum sample size formula? We can do a couple of things with that. We can say for a margin of error of E% and a 95% level of confidence with no prior estimate, the minimum sample size to estimate a population proportion can be written as a function, where the sample size is n is a function of the margin of error. All right? So notice there, we simply wrote this to be a margin of error value, where E is certainly a positive value. And notice when you graph that, you get a function that's concave up and decreasing. And this graph brings up a couple of important things here. First, we see as the margin of error gets smaller and smaller, the sample size increases very rapidly. And we usually pick this sweet spot in here for our typical domain of margins of error. Typically we talk about finding the minimum sample size when the margin of error is somewhere between 2.5 and maybe up to 5%. All right. So we can take a look at we can gain insight in introductory statistics by using function notation in terms of minimum sample size. Let me talk about one more thing. The idea of confidence level and interval width. Now let me show you what I'm talking about here. And by the way, this goes to the notion of inverse and direct variation. That's another topic we want to talk about in pre-statistics, just so it motivates the kind of thing I'm about to talk about here. Confidence interval width serves as a functional illustration of direct and inverse variation. Let's say we want to estimate a population mean mu. All right? The confidence interval width then is twice the margin of error. Let me show you what I mean by that diagrammatically here. Here's a number line. There's our point estimate. Here's our point estimate with the margins of error. And here I went ahead and put in the left and right bounds. But notice here, the width of this confidence interval is simply, here's a margin of error from our point estimate to our upper bound. Here's another margin of error distance from the point estimate to the lower bound. And so the length from our lower to our upper bound of our confidence interval is twice the margin of error. So we can make functions out of that, right? Let's say we fix the sample standard deviation at 5 and we restrict the sample size to 30. Then, in terms of a critical value, we can write a function of the width of a confidence interval as a function of the confidence level and the confidence value that comes from that. All right? So, and I just did this one in tabular form. Notice the idea that we're getting across here is as the level of confidence increases, so does the width of the confidence interval to kind of cover ourselves, so to speak, right? And the reason being is that this part is a constant, but notice here the critical values increase as we go along. So there is some direct variation at use. Now contrast that with this. Let's say we fix the critical value for a 95% confidence level using the student t-distribution and have again a sample standard deviation of 5. Then we can say that the width of our confidence interval as a function of the sample size looks like this. And notice here, the idea we're trying to get across is that when the sample size increases, the width of the confidence interval goes down. All right, so that's inverse variation we're seeing there. Sample size increases, width of the confidence interval decreases, and the margin of error decreases as well. So let me just conclude here with what I'll call 3 takeaways from our talk today on the role of functions on pre-statistics. First, a preparatory course in pre-statistics aids in student success in an introductory statistics course. Second, a contextual notion and review of functions is an essential part of a pre-statistics course. And by the way, if you're interested in taking a look at what a pre-statistics course looks like, if you just go down to the Show More part underneath the video, I have a link to a sample course outline that you can use, and you can start to develop your own course with that. And third, introductory statistics courses should use functions to develop critical thinking skills and support concepts and properties. So thank you very much. That's the role of functions in pre-statistics.